emerging free part. And the third section will be on flattened signed permutations, in which we will going to see some applications of algebra in combinatorics. So to start with background. Yeah, when we consider some literature here, we can find David Callan, who wrote in 2009 about the flattening operation of set partition. I am happy that I'm presenting my talk here after Olivia did last time, because our work is related very much. So flattening operation on set partition is to mean that we concatenate the blocks of set partition in standard form by removing the separators. What does this mean? If you have this kind of set partition, partitioned into 4 blocks here, which are non-disjoint, disjoint subsets of set of the first 9 positive integers. So flattening means you just first write the set partition in standard form, meaning that your blocks are arranged in such a way that the minimal elements are in increasing order. So we have 1, 2, 5, 6, the minima are in increasing order. And when we remove the separators here, we will get this kind of permutation. And we call this flattened partition. The other one, Tawfiq Mansour in 2015 proved that the number of flattened partitions over n is the same as Bell number shifted. So Bn minus 1 is to mean the Bell number on n minus 1. And in 2020, Nabawanda and others gave a bijection between flattened partitions of the set n and partitions of the set n minus 1. And
is it only me who has lost Fufa?
I was wondering the same thing. I thought it's my network. Fufa? Olivia, can you hear me?
Yes,
Yes, we can hear you.
Oh,
I
so
think
it's-
Fufa has his own.
let me try reach him.
I think he has left. Probably network issues.
Yeah, let's give him like maybe a minute to sort that out. It's quite unfortunate.
Yeah, maybe as wait for him, other people can tell us about their
Oh, yeah, in case anyone wanted to
Sarah,
introduce
please.
themselves.
So my name is Sarah Saltik. I'm a researcher currently in theoretical computer science or automata theory, formal language theory at the University of Warwick in the UK. And if I were to do some other field that wasn't combinatorics, probably it would be either number theory, because I quite enjoy just like with combinatorics, there's like fun problems to solve, which you don't necessarily require major amounts of background in, or else algebra, because I think algebra is quite beautiful and powerful thing. Is Fufa back? Oh yeah, great, good.
Fufa, can you hear us?
okay. Yeah, now I think my connection was interrupted, and I think I'm back now.
Welcome back.
Sorry for the inconvenience. I don't know where you did lost me.
From Saga.
Okay.
2022.
Yeah, there.
Okay. So merging free partitions are partitions in which there is no mergeable block. So we have already studied this class of partitions in our previous work, and the other way of merging free partitions that Olivia and the others have been studying, the one which we call unsorted permutations. I think she has been talking about this topic last time. They are in bijection. So we consider merging free partitions and flattened partitions that are in bijection. This gives us that merging free partitions are also counted by the shifted Beyene numbers. So our goal in this work was to find a generalization of our previous results and that of number one and others in the class of type B set partitions. Having said this much about the context, let me give you some definitions about what I'm going to use in my talk. So we get, in the first place, type B set partitions. For this, we need the following notation. The set consisting of the first n positive integers is denoted by this notation. And if we consider both negatives as well as positive integers and also 0, we use this notation. So this is the set consisting of 0 and the plus or minus 1 up to plus or minus n. With this notation, we define type B set partition. Of course, I'm giving you the standard definition of such type of set partition. And consider the disjoint union of subsets of the set n here, such that the following two conditions hold. We have pi given by pi 0, pi 1 up to pi 2k. And for I greater than or equal to 1, if pi 2i is the same as minus pi 2i minus 1. So when I say minus pi 2i minus 1, it is to mean you have a block and then the negative of the elements of this block. Like if beta is a block, minus beta is the set consisting of minus a, such that a is in the block beta. The second condition is that pi contains one block called 0 block, such that this block and its opponent negative is, pi 0 and minus pi 0 are equal. I will have some example for this. If you have this partition of 9, you can see that it is written in standard form, meaning you can see here the first subset here or block is the 0 block because it consists of 0, as well as if there is an element a, it is negative is also here. So maybe I'm using bar here for minuses. So minus 4, I write instead 4 bar. And you have the block consisting of minus 1, 8, and also the negative of this 1 and the minus 8, minus 2, minus 7, 2, 7, minus 3, minus 6, 9, 3, 6, 9 bar, 5 bar, 5. So this is type B set partition over 9. As you can see from this partition, it's lengthy. Due to Adler, we can have very nice code that we can represent the type B set partitions. And we have the following definition. So from the given type B set partition, we remove the barred elements from the 0 block and keep only blocks in which minimum absolute value is positive. We call this element minimal element. Elements in a block are written in increasing order of absolute values, and blocks are written in increasing order of the minimal elements. So considering the above partition here, it can be reduced into this one. This is because if I know 4 is in the 0 block, I can immediately identify that -4 was also in this block. And I just keep those blocks with minimal absolute value, like out of -1, 8 and the 1, -8, I just keep 1, -8. And out of these two blocks that are negatives of each other, we just keep the one with a positive minimal element. So 2, 7 is kept. Out of these two, we just keep 3, 6, 9 bar, and out of these two, we keep 5. So this is due to Adler, and this lengthy representation of set partition can be shortened into this form. Okay. Let us denote the set of all type B set partitions over N by pi n b. So we find the cardinality of this set to be given by the Dowling number, which is denoted by dn. You can find this in the online encyclopedia of integer sequence, which is numbered as 7401, and this is given as follows. The first few terms of this sequence is 1, 6, 2, 6, 24, 116, 648, and so on. To see what the type B set partitions looks like, we can consider n is equal to 2, so that we have 6 such type B set partitions over 2, and they are these ones. So as you can see, always 0 is in the 0 block. That is how we can identify the 0 block, and the partitions here considers 0, 1, 2, and their bars or their negatives. So these are the 6 type B set partitions over 2. If one wants to count this type B set partitions according to the number of blocks, of course, the number of pair of blocks, because if you have a block, there is also, it is a negative counterpart. So it is good to consider the number of blocks to be a pair of blocks. And this is known to be type B Stirling number of the second kind. As you remember, the number of type A, or the ordinary set partitions over N with K blocks, is counted by the Stirling number of the second kind. So for this one, it is given a name that type B Stirling number of the second kind, and it satisfies this recursion. SBNK is given by this one, and we are interested in the type B set partitions without 0 block. So let's denote type B set partitions without 0 block by this notation. When we say type B set partitions without 0 block, either you have no 0 in your list of integers, or else having 0, you can keep set partitions with singleton block, which consists of only 0 in the 0 block. So whenever you have type B set partitions in which 0 is in a singleton block, for example, in here, these first 3 partitions are those I'm considering as type B set partitions without 0 block. In all of these 3, 0 is singleton. The 0 block consists only 0. And if you consider the rest, the remaining 3 here are those with 0 block containing more than just 0. So if you don't consider the 0 block, or the 0 block contains just only 0, we have this sequence. And this sequence is registered in the OAIS as AA004211. So we have 1, 1, 3, 11, 49, and so on. And one can consider the relation between this sequence and the above one, the general type B set partitions. And the relation is given in the following form. The Dowling number, Dn, or the number of type B set partitions is given by this nice relation, which relates Dn and the Wn here, where Wn is the number of type B set partitions without zero block. If one wants to enumerate type B set partitions without zero block according to the number of blocks, then we have this recursion. And this recursion is almost similar to the one that of type B Stirling number of the second kind. As you remember, it is here, there is no coefficient here, but here it is 2k plus 1. This 2k plus 1 means the plus 1 here corresponds to the zero block. And we have those pair of blocks, that is 2k plus 1. But now we have just 2k, since there is the zero block is disregarded. So this is the recurrence satisfied by this class of type B set partitions. Okay, now let us come to our main topic, which was type B merging free partitions. These are partitions given according to the following definition. So consider pi, type B set partition without zero block. For each I starting from 2 to k, a block pi I is said to be merging if the maximum in absolute value of pi I minus 1 is less than the minimum of the following block. A partition with no merging block is called merging free. So with this definition, let us consider the following partition. Now, for type B set partitions without zero block, we eliminate the zero block or the block which consists of only zero. And we have just the first n positive integers and their negative counterparts. So if you take pi, this partition, you can see that the third block, this one, is merging. Why? The maximal element here is less than the minimal element here. And the fifth block is also merging because the maximal here is less than the minimal here. So these two blocks, the third and the fifth, are merging blocks. What about this one? In here, you don't have merging blocks. So the partition is said to be merging free. Anyone here, the second block has minimal element here, which is less than the maximal here in absolute value. The third block here has minimal, which is less than the maximal here. So there is no merging block. And we call this kind of type B partition merging free. Let's denote this to contain all merging free partitions over n, m and b, and Bn is cardinality. By Mathematica, we can see that the first few terms of this sequence is 1, 2, 6, 24, this one. So I hope you have already recognized that this is similar to the sequence of the Dowling numbers up to shift, because this is greater than or equal to 1. But for the Dowling number, we have seen this sequence for n greater than or equal to 0. As a result, we have the following, meaning the set of type B set partitions over n and the set of merging free type B set partitions over n plus 1 are in bijection. So we have proved this by providing a bijection between these two. And I am going to give you the forward implication or the construction of merging free partition from type B set partition. And let's consider pi to be type B set partition, and we construct pi prime as follows, using the following procedure. First, we remove singleton blocks, and then after removing the singleton blocks, going from k to 0, we move mi, or the minimal element of pi I, to the next block I plus 1. In this case, we have to note that the last block, minimal of the last block, will create a new block. The third procedure is that if you have non-zero element in the 0 block, then move it to the rightmost block having minimal element less than a and bar it. Or if a is singleton block in pi, then we insert it in the rightmost block of minimal element less than a, and then finally increase every integer in absolute value by 1. So this procedure ensures that the resulting partition will be merging free and on size n plus 1. Let's see an example for this. Take this type B set partition over 11 here. So we have 0 block consisting of 0, 3, 6, and 2, 4, and 11 are singleton blocks. So by our first step in our procedure, we remove these singleton blocks. 2, 4, and 11 will be removed. And then we have pi star here on the remaining blocks. And starting from the last block of pi star, we move the minimal element to the following block. So this minimal element 5 will create new block here. And then after that, we move 1 here to the next block so that we have 1, 8, 10 bar. And the 0 is minimal here. We move it to the next block, obtaining 0, 7 bar 9. So this is the resulting partition. And then we move elements of the 0 block. There are 3 and 6 in the 0 block, which are different from 0. So each of them will be moved to the rightmost block with minimal element less than them. So 3 will be moved to this block because it has minimal element 1, which is less than 3. 5 was not less than 3. So we move 3 here, and after moving it here, we bar it. And 6 will be moved to the last block because the minimal here is 5 and it is less than 6. So we have 6 bar in the last block. In the next step, we restore the singletons. Singletons in pi, 2, 4, and 11 will be inserted in the rightmost block with a minimal element less than each of these. So 2 will be moved here. 4 will be moved here again because it has minimal element 1, which is less than 2 and 4. But 11 will be moved to the last block because the rightmost block here having minimal element less than 11 is this one. Finally, we increase every integer in absolute value by 1, obtaining this partition. And you can check it is merging free, and the size is increased by 1. So why it is merging free? Maximal here in absolute value is bigger than the minimal here. Maximal here is bigger than minimal here. So the resulting partition is merging free. And this procedure is reversible so that the construction is bijection. And as a result, we have the number of type B set partitions over n and the number of merging free type B set partitions over n plus 1 are equal. Okay, let's consider enumerating this type B merging free partitions according to the number of blocks. To do this, we need to recall the type A or the ordinary version of this concept. So ANK represents the number of type A merging free partitions over n having k blocks. you can refer to this work of ours that ANK satisfies this recurrence relation. And now the number of type B merging free set partitions over N having K blocks satisfies the following recursion. So BNK is given here by 2K, Bn minus 1K plus 2 times N minus 2, Bn minus 2K minus 1. And we have proved this recursion by just observing the type B version is 2 to the power of N minus K times the type A version. And after this observation, you can apply elementary algebraic manipulation to this recursion to obtain this one, the type B analog. Further, if you consider subclass, we have already enumerated type B merging free set partitions. Now here we consider subset of this set according to the following. So let us consider merging free type B partition such that if there is a barred element in a block pi I, then it is the maximal element of pi I, and all elements of the last block are unbarred. For instance, for N is equal to 4, the elements of this subset are the following: 1, 2, 3, 4, 1, 3, 2, 4, 1, 3 bar 2, 4, and so on. Here, there are 9 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. But in total, in type B merging free partitions over 4, we have 24 of them. Out of those 24, we have just 9 of them here with this condition. So you can see here, if there is barred element, it is just the maximal element of the corresponding block. But always, the last block has elements that are unbarred. We will use this class of type B merging free partitions later on, but we can enumerate this subset of merging free partitions according to the number of blocks so that we have the following recursion. B tilde NK, the number of type B merging free partitions having K blocks in this subset satisfies this recursion. So the difference between the original recursion, here the factor K has no 2. In the normal one, we have 2K, and here 2 times N minus 2. In here, you have just K, not 2K. The only difference is this one. Okay, let me take you to another important concept in combinatorics, maybe not only in combinatorics, but also in analysis. It is about rerootedness. If you have 2 polynomials, say f and g, that are polynomials with positive leading coefficients, with roots, say f has fi and g has gi, we say f interlaces g. In this case, we write f with this notation g to mean f interlaces g. If the degree of the first polynomial f is 1 less than the degree of the second polynomial g, assume that it is d here, and that the roots alternate. We have g1 less than or equal to f1, less than or equal to g2, and so on. If this condition is satisfied, we say the 2 polynomials interlaces, specifically f interlaces g. And let's consider the following generic recurrence relation. Suppose C and K are numbers defined in this recursion, and also consider it is generating polynomial function P and T by the summation C and K T to the power of K over all possible K. Then one can easily see that this generating polynomial has this differential equation, given by this differential equation, where p prime here is the derivative of this polynomial Pn, and we have this recursion. And all of these polynomials interlace each other, meaning pk interlaces pk plus 1 for all k greater than or equal to 1. And this proposition can be proved by applying the Rolle's theorem, which we all know in calculus, and applying the properties of real-rootedness of two polynomials and a polynomial and its derivative. So here, by examining the proof, if we apply this to equations in 4, 5, and 6, meaning equation 4 was the recursion corresponding to ANK, the number of type N merging free partitions, BNK, number of type B merging free partitions, B tilde was type B merging free with additional conditions that in a block, if there is barred element, it is the maximal one, except the last block. So when you apply the above proposition to these recursions, one can see that they are all real-rooted. Of course, the fact that ANK, the polynomials corresponding to ANK, are real-rooted was proved by Nabawanda and Alexanderson in their previous paper. In this case, we have proved BNK and the BNK tilde will also result in real-rooted polynomials. This is one result we have obtained considering merging free type B set partitions according to the number of blocks. The other thing we have considered was non-crossing. As you remember, in the theory of set partition, non-crossing partitions gives us classical subclass of set partitions that are counted by the Catalan number in the case of ordinary set partition. We have also considered...
Fufa, just a minute, sorry for the interruption. Just a reminder on to check on time. Have like 10 minutes left.
Okay, so I will be fast a bit. So type A version of non-crossing merging free partitions having k blocks is enumerated by this binomial coefficient, and the total number is given by 2 to the power of n minus 2. We have enumerated type B non-crossing merging free partitions, and one can represent non-crossing partitions by using this kind of graphical representation, so that these arcs are obtained by joining elements of a block. For example, you have 1 to 8 bar in a block, so 1 connected to 2 and the 2 is connected to 8 bar, but you need this ordering. We were using the ordering 1 less than or equal to 2 up to n bar. Then the number of type B non-crossing merging free partitions having k blocks is given by this n minus k plus 1 times this binomial coefficient. And we proved this by considering the following procedure. Maybe I skip the proof idea to come to this one. And the total number of type B non-crossing merging free partitions is given by 2 to the power of n minus 4 times 3n plus 1. Okay, now let us go to the third section of the talk, which depends on flattened signed permutations. And let's define how we obtain signed permutations that are flattened. We first start with type B set partition over plus or minus n without 0. So we flatten it means we just remove the separators to obtain signed permutation. So this partition corresponds to this signed permutation. For type B permutation, we define modular run, which if it is for ordinary ones or type A permutation, it would be just run, but here we consider modular run. In short, we have M run here in this case. It is a maximal sequence, sigma I up to sigma I plus j with this condition. In absolute value, increasing maximal sequence is defined to be modular run. And we have bottom for it is starting point, and that is terminal point is said to be top. We define descent and the measure index. These two statistics are defined in a similar fashion as the ordinary permutations. Descent at I, if sigma I is greater than sigma I plus 1, and measure index is the sum of all index I, where I is a descent. So let's take this set to denote the set of permutations obtained by flattening type B merging free set partitions without zero block. So if you take Dn to be the cardinality of this set and the Dnk enumerates the flattened signed permutations having k descents, we have these first few values of Dnk. So as you can observe here, it looks like symmetric, yeah, but it is not that of Eulerian. They differ starting from here up to n is equal to 4. It looks like the Eulerian table, but it is a bit different here, but it is symmetric. The interesting part is that it is symmetric. When you sum up this table, you will find this one, the last column. As you may recognize this, it is shifted Dowling numbers. So our Dn, the number of flattened signed permutations, is the Dowling number on n minus 1. And the main result here is that Dnk is equal to Dn n minus k minus 1, or the descent distribution is symmetric. So we have proved this, and also considering the joint distribution of descent and the measure index, we have again symmetric distribution. For that, we have this specific generating function, so that GNQT is this, and it is the same as this one, but Q to the power of minus n, T to the power of minus n here. When we also consider counting the number of flattened signed permutations according to the number of descents, we have this formula, which incorporates binomial coefficients and ordinary run-sorted permutations, or equivalently merging free partitions. So we have proved that this number equals this summation. And another way to look at this is this recursion. We have a bit complicated recursion here for the number of signed permutations having k descents, but we have managed to prove this. The idea proof is by just considering any flattened signed permutation and observing sigma 2. Sigma 2 can be plus or minus 2 or different from plus or minus 2. If it is plus 2, then you can delete sigma 1 and reduce everything by 1 in absolute value to obtain the first term here. There will be no change in the number of descents. If sigma 2 was 2 bar, then we delete this and again reduce every integer by 1 in absolute value. But in this case, the number of descents will be reduced by 1, so that we have k minus 1 here. And this complicated sum here come from the case where sigma 2 is different from plus or minus 2. So carefully analyzing this case, if sigma 2 is different from plus or minus 2, then you can find 2 somewhere else at index I. But in this case, one important observation is that 2 is always unbarred because it will start a new M run, modular run. So you can partition into 2, the part before 2 and the part consisting of 2 and after 2 by deleting this prefix and then standardizing, you will be in this set so that this part will come up. Now let me take time to talk a bit about value hopping. For this, we need the following permutation statistics: peak, valley, double ascent, double descent. I hope the definitions are clear. We have peak at sigma I if it is bigger than its neighbors. Valley if sigma I is less than its neighbors. Double ascent if we have 2 step ascents, and the double descent if we have 2 consecutive descents. So taking sigma 0 to be minus infinity and the sigma n plus 1 to be positive infinity, we define the set of peaks, the set of valleys, double ascents, double descents, and their cardinalities. And there is an example here. If you consider any flattened signed permutation, it has always the same number of peaks and the same number of valleys. The other thing is that Z2n action on the symmetric group, which is commonly known as modified Fuata sterile action, or it is called value hopping. We follow the same procedure of Z2n action on the symmetric group sigma n to define a group action on our class of permutations here, the set of flattened signed permutations. And this group action induced by involutions which toggle between double ascents and double descents. So if we have double ascents, then by applying this group action, we will have involution which transforms double ascents into double descents. How do we define this action? Consider any flattened signed permutation sigma. If you have letter X, it is either bottom of an M run or not. If it is bottom, it is always unbarred. So using this, we define the following mapping: psi I from this to this itself, according to the following definition. So sigma I of sigma, I mean psi I of sigma, is this one. We just bar sigma I if sigma I is not bottom of an M run, otherwise we preserve sigma. So for all ij in N, this sigma psi I is an involution, and 2 psi I and the psi j are involutions which commute with each other. Also, we can define for any subset psi s as the involution given by the product of psi I for I in S. For example, if you have this sigma and S consisting of 237, then psi S or psi 2 psi 3 times psi 7 of sigma is given as follows. First, we apply psi 7. Psi 7 means you look at the position 7, which is 4. 4 is bottom because it is starting this run, M run, and therefore we do nothing. We have sigma and it is inverse under psi 7 are the same. And then applying sigma 3 here, I mean psi 3, the third position is 8 bar. So according to our definition, we bar this means we have positive 8. And applying psi 2 at position 2, we have 3. So we bar it, getting 1 3 bar 8, 2 6 bar 7, 4 5. So this is how we apply this involution in our set of flattened signed permutation. So this set for any subset of n define a Z to n action on our class of permutations. Specifically, when you have S is equal to the whole set n, you will see that double ascent of the image of sigma under psi s is the same as the number of double descents of sigma. And the number of double descents under psi s of sigma equals double ascents of sigma. So in this case, we say our involution toggles between double ascents and double descents. And we call this group action, as it was already given in previous work, valley hopping. Now using this valley hopping, we prove gamma positivity of the descent distribution over our class of flattened signed permutation. For that, let us first define orbit. Orbit of the given flattened signed permutations tau is given by this set. So the first observation is that the number of orbits under the valley hopping is given by the Bell number Bn minus 1. The idea of the proof here is we used the average number of fixed elements under this valley hopping, because the number of orbits is the same as the average number of fixed elements under the group action. So since the valley hopping define a Z to n action on Rnb, it has cardinality 2 to the power of n. We are considering any subset of this set S, n. So that is equal to the number of subsets, 2 to the power of n. And then if we define fix of our valley hopping psi s to be the set of all fixed elements, then what we are going to prove is that the average value of fixed elements means 1 over 2 to the power of n times this summation is equal to beta Bell number Bn minus 1. So by counting fixed elements, we were able to prove that the number of orbits is given by Bn minus 1. So using this, we have the following main result. It is given by this theorem 19. The distribution of descent over the set of flattened signed permutation is given by this one. As you may have recognized this, it is one of the instance of gamma positivity. So B tilde here is the gamma base. We have already defined this one. We have proved that the descent distribution is gamma positive. And in addition, we have also the combinatorial interpretation of the gamma base here, B tilde, which is given by the number of type B merging free partitions with K blocks, such that if there is a barred element, then it is only the maximal element of a block, except the last one. So we have proved that this by using first, we distributed descent over any orbit, any arbitrary orbit, and then this is given by 2x to the power of k minus 1 times 1 plus x to the power of this one. And distributing descent over a specified number of Rnk here. I didn't mention Rnk. Rnk is the set of flattened signed permutation having k descents, and it is given by this one. So from the orbit equality equation here, you have Ank, where Ank is the number of unsorted permutation over n having k runs. And therefore, combining these two, we have this one, due to the relation between Ank and Bn plus 1, I plus 1 tilde. So What does this gamma positivity implies? In one case, we have this real-rooted result. The descent distribution gives us polynomials which are real-rooted. And also, in advance, gamma positivity implies the symmetricity of the distribution. So the descent distribution, due to that it is gamma positive, we can say that it is symmetric. So this is all. Some open problems. We were thinking of lattice, poset of merging free set partitions, both type A and type B, under the refinements of blocks, and also relations with ordered partitions and possible extension. Also, some generalization of these results into colored permutations. Finally, there are some references here, and I would like to thank University of Paris Cité and IRIF Laboratory for their generous support for my recent research visit to Paris, and Kotabe University of Education for allowing me or granting me leave of absence during my visit. And I would like to thank you all for your attention. Thank you. Back to Yvonne.
Thank you so much, Fufa. It's been quite a good talk. You can see you also doing work on set partitions. I've really enjoyed the talk. I know time has run out, but we can open the floor to anyone who might have a question directed to Fufa, or if you need to do some collaboration with him, the floor is open at this moment, but hopefully will not take long. I know we are running a bit late, but at this juncture, if there is anyone who has a question, can raise your hand so that I can see from my side and we can have you ask a question.
Yes.
Yes, I can see there is a question. Yes, please.
Okay, great. Thank you for your wonderful presentation. I really like it a lot. Now, I want to ask a question about first the flattening partitions that you talked about at the beginning, that example that you gave. So we discovered that if you look at it closely, so we can, that block that we have, so you can associate with the permutation in S9, right? So the question I'm asking is that, okay, are you going there? Yes, the first, at the beginning. Flattening partition at the beginning, yeah.
This one.
Yeah, the example that you gave. Yes, that example one. So now we discovered that this set partition that you have now, it can be turned to integer partition, and that would be 3321. Okay, so and we have the permutation in S9 there. So, and I'm looking at it that if you look at that, so it means the filling of this partition, integer partition 3321. So in the say row strict now, so it's actually the permutation that we have in S9. Yes. So now I'm asking that, can we do the same thing, that concatenation? Can we do the same thing with a sign, flattening sign permutation that you described, type B, that we described? That is the first question. And the second question is this. So we know sign permutation, you know, these are the elements of a hyperoctahedral group. Okay, in fact, we call it the type B or type C for people who understand the root system. Okay, the Y group of orthogonal group. Now, you came up with this idea of Eulerian, which I don't understand, because we know that when we talk about the counting of the hyperoctahedral group is n, I think 2 raised to the power n multiplied by n factorial. So I don't know how the Eulerian actually come out in that case when you talk about the descent. So I just want to explain those two things to me. Thank you very much.
Would you please repeat the second one, the part that you related the descent distribution into the Eulerian one?
Okay, the first question, what I'm saying is that this question that we have now, so even though you say it's in increasing order 1, 3, 9, 2, 4, 7, 5, 8, 6, increasing order each block. So I'm saying that I can associate to it an integer partition. An integer partition that I have there is a 3, 3, 2, 1. That is the integer partition that gives this set partition. Okay, so I'm not saying that on the right hand side, this is a permutation in one line notation in S9. Okay, so there is a correspondent now between what's it called, between row strict tableau and this permutation that I have there, because I can associate this now. I can feel that the Young diagram of 3, 3, 2, 1, I can fill it with this one as a row strict. Right? So I'm saying that can we do the same thing also when we are dealing with the hyperoctahedral group?
Yeah, for this case, I feel like it is possible to do, even though in this work we didn't take time to look at it. I remember I started looking at the concept of the merging free, type A merging free set partition when there is no sign, but didn't take time to consider the type B case. But I have the feeling that it could be possible to associate with the integer partition as you have observed from this one.
Yeah, thank you.
If I may ask a quick question.
Yes, go ahead.
Hi, Fufa.
Hello.
The sequence of Dowling numbers.
Yeah.
Now you have shown that apparently it is that the merging free type B set partitions have the same sequence. Right?
Yes.
Yeah. So I'm just, what about the entire type B set partitions? Because I'm asking this because of what is in the Sloan entry. It says this the Dowling number sequence. This is the number of type B set partitions. Do they have the same sequence? That is the entire type B set partitions and the merging free. Is it the same sequence but shifted? That kind of situation occurs in compositions. You know, yeah. Is it the same but shifted?
Yeah, after shift, they are exactly the same.
Okay, okay.
So for n greater than or equal to 0, we have this sequence, which is Dowling number.
Sorry for that, I've muted. Go ahead.
And when you consider type B merging free as well, you have the same sequence up to shift. Now we have n greater than or equal to 1 here. Yes, they are the same.
Oh, okay, okay. Great, okay. Thank
Fufa,
you.
there's a question for you on the chats from Stephen Boyer. He's asking, he's saying, Fufa, thank you for the nice talk. Have you considered some Q generalization of these combinatory coefficients, like Q deformed analog of Dowling numbers and some of the recursions therein?
The answer is no, but it could be one possible area to investigate the Q analog. But for this work, we didn't take a look at the Q analog or Q expansion of that.
Okay.
Thank you.
May I say something?
Yes, please.
Oh, thank you so much for the talk. Judging from what you've done, there is also an analog on the other side of set partitions where you are taking a set, right? And then you are partitioning the set, and then you're coloring the set with a number of colors except one element. Maybe it's the smallest element in the block. So in your case, which is the Dowling numbers, the number of colors is actually equal to 2. So you're actually having a set partition. You're partitioning the set into a certain number of blocks, and then in each of those blocks you are coloring the elements with 2 colors except one of the elements. Maybe what you can look at is you may have some nice closed form for these type B merging free partitions in terms of the Stirling numbers of the second kind, because actually they are set partitions
You
in a
come
way.
to understand. Okay, I've looked. Hey.
Are you saying something?
Sorry.
No, go ahead. I think it's an
Then you come
interruption.
to
Okay, so yeah, so even I think this can also be generalized by not just looking at 2 colors, maybe looking at several number of colors, and then you are kind of partitioning the set, and then you are not coloring one of the elements. Then it will be given by the generalized Dowling numbers with M colors. Yeah.
Yeah, this is nice. And we were also thinking of this generalization to any number of colors. As you mentioned, this discussion can be interpreted into using 2 colors that we have used, positive and the minus.
Yes, because it's a 2 coloring problem
Yes,
as it stands. Yeah.
Thank you.
Fufa?
Yes,
Yvonne,
sorry.
through
Yes.
you,
Yes.
Chair? Yes.
Yes.
Yeah, Fufa, thank you for the presentation. So I just have a simple question about undersigned permutations. You talked about the joint distribution, and you are considering 2 statistics, that is the descent and the major index. Yeah, did you have any specific reason as to why? I think it was on slide 14. 14.
1-4.
1-4 here.
When you get in touch with it, you can organize and see what makes you.
No, maybe
I
undersigned
think,
permutations.
Yeah, it is
I don't
this
remember.
one. About descent and the major index is this one.
Yeah. Did you have any specific reasons as to why you decided to consider those 2 statistics together? Was there something striking between them?
Yeah, thank you. The reason is that this table shows that we have symmetric distribution, and this the distribution of descent over our class of permutations. And when you also consider the joint distribution of descent and the major index, you have as well symmetric distribution. And that is the only reason, because we like symmetry, and we have a very nice result that the distribution of descent is also gamma positive, and the polynomials are real-rooted. If you have polynomial that is real-rooted, it implies the low concavity as well as the unimodality of the coefficient, the sequence of the coefficients. So that is the reason why we are interested into the distribution of distance and the major index.
Do we have any other question for Fufa? I can see there are a number of appreciations on the chat messages for Fufa. Thank you so much, Fufa, for taking us through today. It was quite an interactive session. Since there are no more questions that are left, and with time, we are at 3:23 East African time. It's in order we end our meeting for today here. I want to appreciate everyone. Thank you for your time. Thank you for joining us in. Stay alert. We'll be sending out our emails for the next presentation. Remember, our conferences are always on the last Thursday of every month. So I hope to see you all in the last Thursday of September. Otherwise, have a nice afternoon.
Thank you very much.
Bye.
Thank you. Thank you so much. Bye.
Bye. Bye.